Well, thank you so much for having me, and I'm delighted to be with you. And what I would like to do is spend the first part on what the issues are, and then the second part is what we actually should be doing about all these issues. And the way I'd like to start is to give you a brief introduction about climate variability and what we're expecting. I would like then to tell you a little more about what land use is doing. And then in the after the break, we'll talk all about innovative ways of solving the problem. So just to entertain you a bit, do you know this guy? Well, let me tell you a bit of a story. This guy doesn't believe in free trade, but he sells bottled water from Canada. You know, I collect bottled water labels because I'm always interested to see what they put on the label in fine print. And some of it is totally ridiculous. So what is he telling the Americans when he sells the Canadian bottled water? 0% fat and 0% carbohydrate. Doesn't he know that Canadians don't put fat in bottled water? Anyway, this is just for entertainment. So this is what climate change is telling us. Climate change is telling us we're going to have warmer temperatures, you know all that. We're going to have very uncertain precipitation. We're going to have earlier snow melt. We're going to have accelerated glacial melt. We're going to have a lot of rain and snow events. And obviously this is going to change the way the rivers will respond. And so what we really need to think about is climatic variability. And I think we have done a really poor job telling the public that the average temperature is going to change by 2 to 3 degrees. To me, this is absolutely nonsense, because my definition of average is your head is in the oven, your feet is in the fridge, and your belly button is average. If you walk out from here over there and there's 2-degree differences, you won't even notice it. But what you really worry about is when it's too hot, too cold, too dry, or too wet. And so we need to really point out to people that this is the big challenge. So I worked with Alan Hamlet at the University of Washington, and he modeled the whole Pacific Northwest. And what he did, he used 12 different climate models, and we projected all the way to 2100. And what is interesting, if you look at the top graph, this is the temperature trend. And you can see the temperature trend goes all in the right direction. There's a bit of a difference by 2 to 3 degrees. But look at the bottom graph. This is the projection of precipitation. And some models are telling us it's going to get 25% wetter. And some models are telling us it's going to get 20% drier. So that's almost a 50% variability, and we're now telling the decision makers, this is what you have to work with, and they're going to tell us, we can't make decision on this uncertainty, go back and do more research. Well, we can't do more research because it's happening, so you're going to have to live with this kind of variability. So I'm going to take you to the Rocky Mountains and to the Columbia Basin and give you some idea what is happening to climate change in that part of the world, which should be of interest to you. So what I'm showing you here in the top line is the extreme temperatures. The bottom line is the extreme minimum temperatures and the mean, the average. And we go from January, February, March. And you can see what is interesting is the minimum temperatures are increasing far faster than the maximum temperatures. So this is January, February, March, and then we go to April, May, and June, and you can see all of a sudden the maximum temperatures are not changing at all. And then we go to June, July, and August, and September, and it's still the minimum temperatures which are really increasing the most. And then the next thing you want to know is we now know that the high mountains are actually warming up faster than the lowland. If you look at this chart, on the one axis is the elevation, on the bottom is December, January, February, March, April, May, and so on and so on. And you can see the higher elevations are actually increasing faster. And this is bad news, particularly for people in Calgary, because you rely on the snowpack on the ice in a high elevation. And the big challenge we have is we virtually have only a very few stations where we measure climate at high elevation. In fact, out of the 300,000 climate stations we have around the world, only 1% is above 2,500 meters. So we have to do a lot of guessing. So the next thing which you should probably look at is precipitation. So we now look at January, February, March, and the red line is the snow and the blue is the rain. And you can see in January, February, massive decline in snow accumulation. And this goes then into April, where it's stabilizing. And then look at the summer precipitation. It's pretty stable. And then in the fall, you're going to get less and less. So obviously, with all this uncertainty, the precipitation is going to be the big challenge. So if you look at this in the Kootenays, so on the left side, on your left side is the West Kootenays, on the east side is the East Kootenays, and we do from January all the way to December. This is the increase in temperature over the last historic period. And all the red lines are massive increases, and all the white and blue ones are decreases. And what happens in this part of the mountains is the January temperatures are really the big problem. That's where everything is increasing. And it's increasing in some places by 7 to 8 degrees. This is massive. If you look at precipitation, the blue part tells you how much more precipitation is occurring when. And if you look at this, you can see the spring precipitation is actually increasing most. And that should be of real interest to you, because when did you have your big flood? In June. And I will show you, we have the same problem up in the mountains. June is always much more wet and creates far more runoff than on any other month. So that gets me to how we explain climate change. So if you're an academic, you grade your students on a bell-shaped curve. So some of them are not very smart. They're down here. And so you are all up here, right? You're very smart. And so when we now talk about climate variability, we also put it on a bell-shaped curve. And so historically, the blue line is what has happened to climate data. And now, because of climate warming, we're saying we're going to get a shift from the colder to the warmer. But here comes the interesting part, because now we have if we go back to the classroom, we're going to have a lot more dumb students and a lot more really bright students, or in the climate situation, we got lots more cold conditions and lots more warm conditions, which means this bell-shaped curve becomes flatter. So it reduces from this to this. And then we shifted to this, which means we're still going to get a lot of cold events, but we're going to get more warm events. And this is really critical to climate change variability. So the average isn't changing very much, but if you look at the East Coast right now, they have had some massive cold periods, very short cold periods, and we have had the warmest spring ever. And so this variability is increasing. And if you look at the climate data for North America, the average is exactly the same, but the variability is changing. Okay, so is this variability actually increasing? Here's a graph which shows you the temperature and the precipitation over a 100-year period in Texas in 2011. And all these dots are a 100-year record, and in 2011 it was very far out of norm. I mean, you can see this is not just if a bell-shaped curve, this is 2 orders of magnitude out of the bell-shaped curve. So is this happening nearby? Here is an example from Colorado, and remember they had a big flood the same time as you had a flood, but in September. And here's a 100-year record of Boulder, Colorado. I went to university there, so I have some interest in it. Look at what 2013 produced. And they had a flood which is probably equally as big as yours. And so if you look at the annual record, the bottom line is the yearly precipitation, and this was 2013. And if you look at the upper part, this is the month of September, and this is what happened. And what is even more interesting is this. This is the daily rainfall record. And so if you look at the top graph there in 230 millimeters in 24 hours, but they have rains continuously. So you can see in one day they had 230, the next day they had 290. And so in 3 days they had 340 millimeters of rainfall. And there is no way the soil can handle that kind of thing. No matter what you do, when you get that kind of incident, you're going to have to start storing that kind of water. This is Kaslo in the central Kootenays or in western Kootenays. So when we do stormwater design, we have the 100-year record, right? And we base everything on a 100-year historic record. And this was the highest here in 1963. We got the highest precipitation in the middle there. In 2005, 2012, and 2013, we had 3 incidents which were between 30 and 70% higher than anything we have ever experienced in 100 years. That should be a wake-up call for people. And remember, your IDF curve, intensity, duration, frequency curve, which every engineer uses, is all based on historic periods. And that historic period is no longer valid. And so we need to re-engineer the 100-year record and the IDF curves, and this is going to be quite a challenge. So is the variability in precipitation increasing? Here's Creston, and again it's about a 70-year record or a 100-year record, and you can see the variability in terms of precipitation is clearly increasing. And 2015, one of the driest summer on record. So we're getting these extremes which are quite dramatic. So if you look at the central Kootenays, the yellow ones are 3 communities which had some interesting experiences. We have a project where we're looking at water conservation in 20 mountain communities, and we've had 5 years of record now, starting from 2009 and 2010, and now it just finished. I'm just looking at the data. And if you look at these communities, in 2015, the red ones were the driest and the warmest. And so again, this is another example of how the extremes are changing. This is the June precipitation over 100 years in these 3 communities. And the red one is 2015, which was the driest, and the other ones were the peak events. So you can see all of these extreme events, the driest and the wettest, occurred in the last 10 years, and they're far higher than anything which is in blue. So this is a reality check. This is what we really need to focus on. So Kaslo had these 3 storms, 2005, 2012, and 2013. The 13 flood wiped out their whole drinking water system. And just to show you how complicated it is, I'm showing you the daily rainfall event for each one of these storms. So the first storm in 2013 had a really high peak. The other one in 2012 was all over the map. It was just continuously wet. And then the 2005 is a different type event again. So we can't really think of an individual storm anymore. We have to say, well, sometimes you will have something like you had here, a freak storm, but in other cases you might just have too much rainfall. And so this is the real challenge for all of us. So that's the 2012 and gives you a bit of an idea when these things happened, and all in the last few years. So that gets me now to your part of the world, and just to give you a bit of an idea in comparison. So we have the Calgary flood, we have the Boulder flood, and we have the Caslow flood. And that gives you a bit of a difference there in terms of 250 millimeters, a bit more from what I understand. You might correct me if it's wrong. That was your event which created your flooding. Well, in Boulder, it was 341 over 3 days. And in Caslow, it was 100 millimeters in 1 day. So again, this is a really good comparison. Depending on what the watershed responds to, you get very, very different flooding events. So in Caslow, you only needed 100 millimeters to wipe out everything. In your place, it took more than 250, and in Boulder, it took 350. So that gets me to Vancouver. So we are the wet coast. We never worry about water. Every time I give a talk, people say, oh, you're out for lunch. We don't have to worry about water. We get enough rain and don't worry about it. Guess what? 2015 was the driest summer. Here's the record since we started measuring. And panic set in. Nobody knew how to deal with it. And was even more pronounced. I work in a watershed in the lower Fraser Valley, and it has flooded quite a few times, and the headwater of that watershed has a big landslide in the US, which has exposed a deposit of asbestos. And every time we get a storm, it floods agricultural land and deposits all this sediment, which is full of asbestos fibers. So it's a huge health concern. So I looked at the record of storm events, and we figured at about 15 cubic meters per second is when we get flooding. And so I looked at the 50s, the 60s, the 70s, the 80s, the 90s, and the 2000s, and the 2010. And here are the number of flooding events in that watershed, and they're clearly increasing. In 2009, we had a fantastic rainfall event on a classic rain on snow event. And here's the example. The red line is the amount of snow which is accumulating. The high one is what is on the ground, and the other one is the snow falling. And then the blue is the rain. The temperature system went up high enough that it rained on top of it. And then you got this mess here, which I call a horrendogram. And you can see, this is the discharge. And so when you get snow on the ground, and you get cold temperatures, and then rain on top of it, it becomes like an impervious surface. And we got the biggest flood over that period. And this is what the landslide looks like, and this is the flooding. And again, 2009. You see how much higher that is over that time period. So this is a fascinating picture. I've worked in watersheds all over the world, but this has never happened to me before. Here's an incident where the headwaters of the Mississippi were in extreme flood conditions, and the mouth of the Mississippi was in an exceptional drought. These are all the hydrometric stations of the US in 2011 in May, and you can see all the dark colors, the blue colors, where all the stations were in an exceptional flood condition, and all the red ones on the bottom were in an exceptional drought condition. Same time. Usually we have one or the other, we never have both. Fascinating. So what we really should be worried about is floods and droughts. And floods we can predict. we usually get 24, 48, maybe longer advance notice when we might have some problems. So you can actually do something in terms of planning, but when it comes to drought, we never know when it starts. We never know how long it will last. And this is going to be the big challenge, and particularly in California, which you probably heard about. And so don't forget, I know you're all preoccupied now with flooding. I think you should also be worried about drought. And I was invited to an agricultural conference by the irrigators in Lethbridge a few months ago. And I was really impressed in what they were doing. And they were telling me that last year they were extraordinarily lucky because they had very, very dry conditions. And then in August, they got the rainfall at the right time. If they wouldn't have gotten the rainfall, they would have been in trouble. And that's exactly what happened in Vancouver this summer. Until the last week of August, we had the driest conditions ever. Many communities were going to run out of water, and then we had the rainfall. That bailed them out, and now it's all forgotten again. Okay. But there's some good news about climate change. And if you look at the modeling here, obviously for agriculture, this is going to be beneficial because we're going to have a longer growing season. We, in the Columbia Basin at least, we expect slightly more precipitation, but it's a lot of uncertainty associated with it. We're going to have less frosty days. That's also good for agriculture. And we have longer growing degree days. So for agriculture, this is actually quite a good situation. That means we can actually move agriculture into new areas. And lo and behold, this is already happening. For those of you who like wine, you all go to the Okanagan, right? Well, if you now want to start a new farm in the Okanagan, the land is so expensive, nobody in their right mind would do it because you need to have a lot of money because it takes 5 years before you get anything. A lot of people are now moving, 5 people are moving to Grand Forks, and they're starting wine production in Grand Forks because the climate has improved sufficiently. Anheuser-Busch, the Bud people, you guys like beer, right? The Bud people grow all their hops at the Canadian border in Idaho because they looked at all the climate across the US and it mimics the climate of Bavaria. And so that's where they started. They came to us in the Columbia Basin and said, we're thinking of moving north because of climate change. Can you imagine? The Bud beer moving to Canada? Be a good discussion with the candidates, the Republican candidates. Another climatic problem you need to think about is fire. And this is a huge issue. We worked with a number of communities in the Columbia Basin to develop climate change adaptation strategies. And fire always came out as number 3. Number 1 was drinking water. Number 2 was flooding. Number 3 was fire. And number 4 was food security. Those are the 4 big issues. Fire is interesting. The number of fires has not changed. But what has changed, particularly in BC, is the size of fire. So we're getting much greater areas affected by fire, and this has huge implications for hydrology. And this is not only the case in BC, it's in the case of the US the same way. You see the number of fires have actually declined. The area is increasing and the size by the individual fire is increasing. And that's obviously challenging situations. This is last summer, and you probably remember we had a drought in California, in Oregon, in Washington, and also in BC. And you can see where all the fires were. They were concentrated all in this very dry area. And this El Nino situation is quite interesting. You can see how unusual this El Nino was. It was much higher than all of the other El Ninos. And so these are all the extreme events which have happened last year, according to NASA and the climate people in the US. And it's showing you all the crazy events which have happened around the world. So that gets me back to your part of the world. And so what people are doing now is they're looking at how much water is actually contributed from the mountains to the lowland. And what I'm showing you here is an example from a colleague of mine, Vividroli from Switzerland, who looked at major river basins and said, how much of the river basin is actually in the mountain, and how much does the mountain contribute to the lowland? So he calls it the water towers of the world. And if you look at the left-hand side, these rivers there contribute almost 90 to 100% of all the water to the lowland. The Colorado River is an obvious case. And then there's some which don't create as much. But why is this important? Here's an example from the OPPs. So the OPPs represent a very small part of the watershed, but there are 4 major rivers which contribute to the lowland, and this is the proportion, the alpine proportion. So in terms of the Danube River, about 26% comes from the mountains. In the Po River, 53%. In the Rhone River, about 41%, and in the Rhine River, about a third. So obviously, we need to start working on the mountains to preserve as much water as we can in order to create the possibility. But what is even more important is, when is this water actually coming into the lowland? It's coming in the summer when the demand is the highest. So if you look at this, the lowland is the blue line is the contribution from the mountains, and the red line is the total. And you see the contribution from the mountains is June, July, and August when the demand is higher. And that's exactly the same thing for you here in the Rockies. And so let's think about that when we do management. So in summary about the increased climatic variability, we're going to have to worry about wind situations. I didn't tell you much about it, but we have had 2 incredible windstorms the last 3 weeks. And in 2003, we had this incredible windstorm in Stanley Park, where 3,000 trees were decapitated. And I made an effort. I went to, when they cleared the forest out, I went and looked at how old these trees were. And many of them were between 200 and 300 years old. So they experienced climatic conditions over a long period of time and no problem. But this freak event created all kinds of headaches. And so increased extreme events, less snow and earlier snow melt, more freeze and thaw events, more rain on snow events, accelerated glacial melt, reduced summer flow after glacial melt. This is a really big issue because we don't know when the tipping point is on a glacier. We know right now a number of glaciers are melting very fast and everybody's happy because they get lots of water. But when is the glacier too small to create runoff? Glacier National Park in the US, Don Fogre is a good colleague of mine. He has been documenting all the stuff which is happening in that park. When they created the park in the 1900s, there were 125 glaciers. Today they have 25. And their big advertisement now for tourism is, come and see a dying glacier. So, enough of that. So now I'll tell you a little bit about drought very briefly, because I don't want to bore you too much with climate and then get to actions. Again, flood and droughts are important. The impact of drought is really more challenging, because the real challenge for California right now is how long is this going to last? You can overcome problems for 1 or 2 years, but if it's longer than that, that's going to be quite difficult. So there's 3 different types of drought which you need to think about. One is called the meteorological drought. That is simply the deviation from the long-term precipitation. But then there is also the hydrological drought, and that is basically the deficit in the supply and availability of water. And then, of course, there's a soil moisture drought. And the soil moisture drought is something which the farmers here know quite well, but I don't think the politicians appreciate that. How do the farmers decide when they're going to have troubles with drought? When the spring soil moisture is at very low levels. And let me tell you a story. Nobody wants to study soils anymore because you've been told from the time we were born, don't get the dirt in, don't eat it, don't deal with it, right? Yet, it's probably the most important component we need to think about when we deal with water management. And I'll tell you in the innovations how we actually do that. So the real option which is used whenever you have a drought, what is the next source we can use for water? Groundwater. California is a classic example where, so we have not enough surface water, we'll go to groundwater. They never had groundwater regulations. So now, last November, they decided to have groundwater legislation. How long do you think it's going to take them before they can actually use the information? 2030. Because they've never inventoried, they never mapped. If you look at the groundwater water table, you can't just look at it for 1 or 2 years because every year in the summer it goes down and the winter comes back up. Well, you need at least 10 years of data to see whether the water table is actually going in a downward direction. So that's going to be 15 years before they actually have the information to make decisions on. And right now they're extracting it far faster than they are actually replenishing it. So that should be an eye-opener for us as well. So here are the bell-shaped curve to show you what drought has done. This is 2003 in Europe. All the lines are the summer temperatures since 1900, and 2003 was way out of norm. And then you went to Australia in 2003 to 2007. The blue line is the Murray-Darling River on a normal year. And at the beginning of the drought in green, it was about there. And at the middle of the drought, it was in the red line. They virtually run out of water in the river basin. And that's the river basin which produces most of the food in Australia. And then in Moscow in 2011, same situation. And then in Texas, I showed you already. So these are the big droughts. And now, if you look at what happened to the cereal price, you can see after every one of these droughts, the global cereal price goes up and up and up. It's clear. Every time we had a drought, some are bigger and some are smaller and so on. So droughts are equally critical. So let me just tell you a bit about California. It's a fascinating situation because they produce probably half of all the food we import in the winter, sorry. They apparently produce about 80% of all the fresh vegetables in the winter for the US. So the Pacific Institute put up some interesting numbers. What crop is using most of the water in California? Everybody will tell you it's almonds. That's totally incorrect. Look at the red one. 50% of all the water in agriculture in California is used for alfalfa and forage, the most low-value crop. The dollars there tell you the dollars per acre feet, I think. Yeah, the dollars per acre feet. So the most water is used for the lowest value crop. And you can see the differences, and there's lots of misconceptions. The one good thing, the most water efficient crop, also in the Okanagan, is grapes. So keep drinking wine. If you look at all the beverages, which beverage uses the least amount of water? Tea or beer? And you know where my preference is. We have a colleague, a former student of ours, who started a craft brewery. And the average business uses 4 liters per liter of beer, 4 liters of water per liter of beer. He is down to 2 liters per 1 liter of beer. So you can actually do tremendous amount of improvements during drought. So you look at the California drought over time, the red line is the percent of California under an exceptional drought, and it's continuing. I've just put it up to June to January this year, right? So we don't know how long this is going to continue, and this is going to be a real challenge. What is even more interesting is the drought has not hurt the economy because the prices have gone up. So the farmers are not really suffering. They're producing less, but their income has not gone down, which is quite interesting as well. However, what is even more interesting is the electricity. California gets about normally 18% of their electricity from hydropower. And now, as the drought has progressed, you can see the blue is the amount of electricity produced under normal conditions. The yellow is under the beginning year of the drought, and now the red is now. They have spent $2 billion to replace this hydropower with natural gas. So the economics of that are quite phenomenal. So if you look at this, these are the kind of lessons we should learn from California. Obviously, they're now going into water trading. So now people are saying, well, if you don't use it efficiently, we need to trade the water. And this is a big challenge for us on the West, in the West, because we have such archaic water laws that first in time, first in right, you can do anything you want. And all of these allocations were given at the time when we thought we didn't have to worry about water. And now we have, at least in BC, I know at least 5 river basins which are totally over allocated. So how are you going to actually persuade people to give up some of their water rights? And this will be a real boom for business for lawyers. But we need to change that, right? So let me just show you a brief example of drought, Sunshine Coast, outside of Vancouver, 15-minute ferry ride, 20-minute ferry ride. This is the water supply for the Sunshine Coast, 25,000 people. In 2012, not last year, 2012, we had a student who did the project on it. He said, okay, what is climate telling us? These are the temperatures in July, August, September, and October over the historic time. So the summer, might I have that right? Oh, sorry, the precipitation, sorry. So this is the precipitation data over the time of we have a record, and you can see the summer is getting much, much drier. This is the temperature. All the summer temperatures are going up. And this is the precipitation in the winter, declining, and this is the temperature in the winter, which is going up. Now that reservoir is in a high mountain, so it relies on snowmelt. So guess what has happened? In 2012, in July, there was still snow up here, and everyone said no problem, right? In August, in September, people started to worry a little bit, and in October it was down to here. And they had pumps ready to go up there, trying to siphon the last bit of water to get it out. So they were totally unprepared for this. And so our student, Monty Stotts, did this study in 2012. And then he went back to his job. And then in 2015, we had the lowest snowfall ever. And if it wouldn't have been for his effort, they would have run out of water. Everything was just at the point where they were on stage 4. Water conservation means nobody was allowed to use any water for outdoor purposes. And the public just went crazy. And it rained the last week in August, and that bailed them out. So this gives you an example how precarious many of these supplies are. And just to show you, this is not just one event. Look at the red points. Over the last 10 years, we have had 3 of these things, and they're going to happen more frequently. And if you look at the summer precipitation, obviously it's declining, so we know what's in store. The same is for temperatures and so on. So we built all the big hydropower dams in the 50s and 60s and 70s, and then all of a sudden said, no more hydropower dams. They are all detrimental. They create all the problems. Guess what? There is a complete re-emergence of hydropower production around the world. China is building hydropower dams you wouldn't believe. California is rethinking storing water. And the unfortunate thing is, I don't think we have learned very much about all the mistakes we made in hydropower development, and we're still doing the same thing over. So whenever we build a hydropower dam, we tell people, oh, this is fabulous recreational opportunity, right? What about this? This is in the Kootenays, right? So if your reservoir is relatively shallow, you're going to have all kinds of problems, and this is not a particularly good recreational opportunity. So are you still okay if we continue? So climate is one thing, but land use is something else. And I don't think very many people have made the connection between climate variability and land use change. And I would advocate or predict that land use changes might be more important than the climate variability. Now, I can never prove that to you because I cannot do an experiment where I can hold the climate constant and change the land use or to do the birth. So it's a bit of guessing. But I will show you examples where we know that if you intensify your city, that impact on the hydrology is far greater than the climatic variability in terms of runoff. So let's see what this means. So what we need to really work in a watershed context is we need to look at the climate variability and the land use changes. Skip that. So this is probably the most important diagram I can show you. I love diagrams. My wife always tells me I shouldn't have too many diagrams. So what I'm showing you here, what happens to land use. So on the bottom, we go from a forest all the way to impervious surface in a city. And what I'm showing you in green is how much of the rainfall evapotranspires. The red is how much of that rainfall runs off the surface. The yellow is how much of that goes into the soil, and the blue is how much goes into groundwater. So if you look at the forest, you see the distribution, very little surface runoff. If you now move all the way to the urban environment, you can see how we change the hydrological cycle. So in a big urban environment downtown, probably 70% of the rainfall runs off the surface. And that's why we have all the flooding problems. So if you look at a typical hydrograph, how the river responds to a rainfall event, the blue line is in a forest, and as soon as you make it impervious, you have the green line, which means, first of all, the river will respond much faster when the rain starts, and the peak flow is going to be higher, and your base flow is going to be lower. And this is really creating more variability and more extreme events. If you want to have fish and invertebrates or anything else in your river, we always say we want to keep salmon in our rivers. If you look at the amount of imperviousness in your watershed versus the biodiversity, the upper corner is very high biodiversity, the lower part is very low biodiversity. And if you look at this, you can see this is a curvilinear relationship, and it doesn't matter whether you use invertebrates or whether you use insect diversity or whether you use another aquatic index. They all show this curvilinear relationship, and what we're saying is if Calgary is down here and you rip off pavement, you can go a long way and have no impact on the river. Can we actually build cities with less than 10% or 15% imperviousness? That's your challenge. And I'll show you how we actually do it. We can actually do it, believe it or not. So this is what urbanization does. On the left-hand side, you see 1984, Coquitlam, and 11 years later, urbanization. All the black part is forest, and all the other stuff is urbanization and impervious surface. So it goes extremely fast, right? And think what that will do to stormwater runoff. So when we look at water quality in this direction and water use, we now say agriculture and urbanization are the big two problems. Agriculture uses most of the water and is now the biggest polluter, and urbanization is not far behind. Remember, 3 billion people will globally move into cities in the next 30 years. That's almost half of the current population. 3 billion, which means we're going to have to re-engineer the way we develop cities. So that gets me to the hydrological cycle, and I divide the cycle into the green cycle, the green water, and the blue water. Are you familiar with that concept, blue and green water? Well, the blue water is the rainfall which hits the surface, runs over the surface, and ends up in rivers and lakes and reservoirs, and some of it seeps into groundwater. That's the blue water. That's the water we use. That's the water we manage. That's the water you drink. And then there's the green water. That's the rainfall which hits the vegetation, goes into the soil, and gets picked up by the vegetation and evapotranspires. How much water do you think goes through the blue cycle, and how much goes through the green cycle? Have you ever thought of that? 2/3 of all the rainfall goes through the green cycle, and only 1/3 goes through the blue cycle. So why don't we start thinking about managing the green cycle? We don't manage the green cycle. We grow rice in California in the middle of a desert. That's not green water management. So why don't we start thinking about using that green water concept? If it's 2/3 of all the rainfall, there's some wonderful opportunities in the urban stormwater business where we can actually use this concept. And so if you look at this, 100%, 65 goes through the green cycle and then gets evapotranspired, and only this part goes into lakes, rivers, and groundwater and then gets back up. This is my horrendogram. But I'm trying to show you how complex it is to manage urban water. We're dealing with stormwater runoff, domestic wastewater, industrial discharge, accidental spills, solid waste, atmospheric pollution, and water supply. Very complicated way of doing business. Now, there are two groups in every city who treat water, the wastewater people and the drinking water people. Do you think they ever talk to each other? You'd be surprised how few times they talk to each other. And so think of this complexity in terms of urbanization. Look at agriculture. Again, very complex situation, dealing with all kinds of impacts from agriculture. And then the foresters are also doing some nasty things. And then, of course, the mining people are doing some nasty things. So now if you live in a watershed, you're going to have all these different land uses to deal with. How do we help integrate this whole business so that everybody is helping the stormwater business and the drought business? So let's have a quick look at some of the things forestry does. Now, forestry does harvesting. They plant trees. They build a lot of roads. And they do, hopefully, some long-term management. We have 200,000 kilometers of paved roads in BC. We have 500,000 kilometers, which is from here to the moon, in logging roads. Well, do you think we built the logging roads the same way as a paved road? Do we manage them? You know, we built them quickly so we can harvest, particularly pine beetle extraction and so on, and then we just leave them. So they generate massive amounts of sediment. And if you're really concerned with health, I'll show you this interesting picture here. We did some studies on how many pathogens are in the clear water, how many are in the suspended sediment, and how much are in the bed sediment. And when you look at the numbers, look at how many pathogens. They're orders of magnitude higher in the suspended sediment because you've got biofilm, and they can actually, you know, that slimy stuff. If you pick up a rock in a river, it's slimy. That's the biofilm. And they can actually hide in there, and that's a perfect environment for them to survive. So if we can reduce the sedimentation and the pollution from turbidity, we can actually help the health situation for drinking water dramatically. So what does forestry do? Here's a very good example. The upper watershed, the Greta watershed, wasn't logged very much, about 5%. And the lower watershed, right next to each other, was logged and had about 40% clear cut. And Dan Moore did this nice study, and it's in the Okanagan. And so he looked at the discharge of these two watersheds before they logged, during their logging, and after logging. And let me show you how this changed the things. So the red one is where they logged the thing, and the green one where they didn't log very much. And if you look at the early part, this part here was before the logging. And you can see the two patterns match reasonably well. Then they logged, and then see what happens to the red one. And then about 7 to 10 years later, they're back. So we get about a 7 to 10 year window where you change the hydrology and then the forest recovers. So if we do a lot of logging, this has some real interesting concept. Yes, we can restore it, but it takes quite a bit of time. And in the meantime, you might have a huge problem. And I will show you later on what we actually should be doing in the mountain part to actually increase the storage capacity of water so that you have the runoff in the summer. Of course, you heard all about the pine beetle problem, which they have now eaten themselves out of food. But it covered an area twice the size of Denmark. And so the government was at a dilemma saying, what should we do? If we leave it, it's a huge fire hazard. If we harvest it within 2 to 3 years, we can still use the wood. It's not hard enough. And so risk, well, log. So we logged landscape size areas, and I don't think we have very much idea what this will do to the hydrology, because all the research we ever did is in a plot study. We never did it on a landscape size, and that's still up for debate. Here's the size in BC which was affected, and here's how the beetles have actually eaten themselves out of food. But what is even more interesting now is all of a sudden we have a new problem, and that is spruce beetle. And I just heard yesterday, apparently Prince George is already panicking about spruce beetle. So all of this is directly related to increased temperatures. And so, again, we have to be prepared for these kind of changes. That gets me to winter recreation. So we do all kinds of wonderful things, right? We all love to go skiing and hiking and snowmobiling and so on. I'll give you an example. This is a classic ski area in Europe. And you think, well, that's all benign, right? It's all doing the snow wonderful thing. Let me show you what they actually do in these recreation areas. So Whistler gets about 2.3 million people visiting every year. They have about 55% in the summer and about 44% in the winter. They have 200 kilometers of hiking trails, 300 kilometers of biking trails. They have 3,000 hectares of ski areas. They have 100,000 rounds of golf. They have ski lift capacity of 35,000 people per hour. They can move 35,000 people per hour. And they have 270 snow cannon to make snow. Now think of this. This is like urbanization. This is no longer looking at the green water management. So if you can't read this, it means snow security for sure. So you're advertising now. If you want to have a business going, you need to have snow at Christmas, otherwise economically you can't make it. So now everybody is saying, well, gee, we can actually do this. How much water does it actually take to make snow? Have you ever thought about that? And when do you need it? You need it in November. So when is the river flow the lowest? Usually August, September, October, and then depending on the snow, right? So it takes about 2,000 cubic meters per hectare of 30 centimeters of base. And that is equivalent to about irrigating an agricultural crop like corn. So it's like agriculture. And I don't think people have ever thought about this. And we need to do more of this now because it's going to get warmer. And so late winter or early winter, we don't have enough snow. Another P of mine, how many of you play golf? Only one, so I'm okay. This is in the Okanagan. We did a study on the water balance in the Okanagan. And as you can see, we now have about, I forgot what it is, about 50 golf courses in the driest watershed in Canada. And the golf people are probably the most conservative people. They don't want to change anything. Everything has to be green, right? Do you know that the golf courses in the Okanagan used exactly the same amount of water than all the wine growing areas? And they don't need to have everything green. I thought I was educated. I don't know much about golf, but I was educated that when they started golf in Scotland, they left everything except the putting area. So why don't we, I sent a letter to each one of these golf courses and asked them whether they could give us some data so we could actually verify our model. Guess how many responses I got? One. 1 out of 50. So that's a culture we need to change. That gets me to agriculture and all the problems with agriculture. And just to give you a bit of an idea what happens when a river comes out of a forest and then goes into intensive agriculture. So in a forest, you have some wildlife. So if you look at the bacterial problem, so the blue is E. coli, and the green is fecal coliform, and the brown is total coliform. So you got a little bit of a problem coming out of the forest because you got wildlife. And then you go into the lowland, and then you go into the more intensive one. So you can see the kind of issues which we're creating. And so the pathogen problem is huge. And I have been working with Judy Isaac at the Center for Disease Control. She dragged me into a completely new area where I know nothing about. And I felt very inhibited, but she said, look, I need you. And I said, well, what for? I know nothing about microbiology. And she said, well, I have a problem. We test all the drinking water in BC, and whenever we have a problem, we tell people to boil the water. And we very rarely go out and find out where this problem is coming from. So she said, well, I have a genome project. We want to go and do the DNA of every pathogen we can find in the water. And if we can identify the origin of that pathogen, we can actually go into the watershed and do something about it. So I was dragged screaming and yelling into this project, and it's been a total revelation. We're now at the point after 5 years where we already have 3 pathogens, one from sheep, where we can actually say, okay, we know the origin, we can actually do something about it. So this is a really interesting area of research, and the changes in that technology has been phenomenal. 5 years ago, we could do about 10 samples a day. Now we can do 3,000 samples a day. So really exciting area, very complex. Now that makes me very unpopular in Lethbridge. I've been all advocating that beef production is not a very good thing to do because it creates all kinds of problems for water management. And if you look at this particular graph here, are the number of cattle in the various in Canada and how many are in Alberta. And this is the export of beef from Canada. So 78% of all the beef produced in Canada, which is exported, is in Alberta. 3/4 or more. So think of it. It's the most water-intensive way to produce food. It creates all the eutrophication and nutrient problem in water. It creates 4% of all the greenhouse gas. But from an economic point, it's the most valuable thing because the demand for beef is going up sky high. China, 10 years ago, consumed 20 kilograms of meat a year. Now they're at 60, all within 10 years. The demand is high. And they are already thinking about saving water. So they let everybody else produce the meat so they can actually save the water and don't have to deal with the pollution. In fact, they just bought the biggest pork operations in the US so that the problem of pollution, the problem of water, and the problem of greenhouse gas stays in the US. And they are importing the final product so they don't have to deal with it. Chinese policy, and I don't know whether it's policy, but the data shows that they are importing only water-intensive food so they can save water for everything else. So this is just showing you how much of the pollution in nitrogen and phosphorus comes from cattle alone, and the red, the yellow, and the brown, and the white is all cattle related. So 3/4 of all the water pollution in agriculture actually from from cattle production. And if you don't believe me, here's Environment Canada's map of the total nitrogen produced in Canada. And you can see where you live. You're the highest producer of manure in terms of nitrogen and phosphorus. You'll never invite me again, right? So I am in this incredible privileged situation that I have access to the youngest and the brightest in society. So what you do is you have lots of cheap graduate students who are very diligent. So you put them into the same watershed every 5 years to see how things change, right? So you can see this is one grad student, that's the next, that's the next, that's the next. And you can now see what happens to the nitrate value over time, because government's monitoring program is really not that good. But these kind of pictures show you the green line is a tributary in a forest, and this is in an agricultural intensive area. So skip that. Now, the other interesting thing to me is ethanol, biofuel, right? The US is the biggest producer of corn, and let me show you what has happened in terms of food export by the US. This is how much food they have exported. In fact, the US used to export 50% of all the corn traded globally. 50% was exported. Look at where they are now at 20%. And this is all because of ethanol. So this is the export of corn. And so they subsidize the biofuel to the point where it is much more attractive for the farmers to grow corn for ethanol rather than producing it for food. And the impact of that is enormous because corn is one of the least efficient way of converting biomass into ethanol. And it's also one of the higher water consuming things. What we actually should be doing is we should let the tropical countries do sugarcane, which is the highest converter into ethanol, doesn't use a lot of water, it's in the tropics. That would be a far better thing to do than this. Look at the numbers which you subsidize in Alberta. I'm going to get into trouble here. This is the subsidy which you put into ethanol. which is not a very efficient way of dealing with the conversion, and it's not a very efficient way to deal with water. Mining, I'm just very quickly, mining obviously, oops, skip that. We have all kinds of problems with mining. You guys are a bit lucky because you got the limestone curtain, which neutralizes a lot of the stuff, so you don't have to deal with this much. But on the other side, where we have some granitic and metamorphic rocks, where we have lots of mines, we have a lot of acid mine drainage problem. So we'll take a very short break, and then we'll go into what can we actually do. I totally depressed you with all the problems, right? And so now we're going to try to tell you what we can actually do. Have you ever thought how much of the rainfall which lands on the terrestrial surface of the Earth per year ends up in the ocean? So if you think of all the rainfall which hits the land surface of the Earth, how much of that water ends up in the ocean every year? Academics do all kinds of stupid calculations, right? Guess. About 30%. And the rest is all recycled, right? So now that I depressed you completely, let's see what we can actually do. So urbanization, this is what engineers have done. They have been told to get rid of the water, and they did a fabulous job. We worked on the water supply of Sao Paulo, that picture on the left. And Sao Paulo is in a basin, and the freeway is on both sides of the river, and they channelize the river. So whenever it rains, the water can only come up. And lo and behold, about 7 to 10 times a year, the water comes up onto the freeway, and then you're stuck. And about a third of the water is sewage. And so I can talk from personal experience. I got stuck for 24 hours in this stuff, which is not a pleasant experience. So we need to start looking at flooding totally differently. And this is now the IDF curve, right? Intensity, duration, frequency curve, which almost all municipalities use. The black line is the historic data. So in a 100-year flood, you got so much discharge. So if we now look at the new climate norm, you can see that we get a 100-year flood probably every 10 years. And that means, how are we going to cope with this? So traditionally, what we have done is we looked at the property scale, the neighborhood scale, and the watershed scale. And at the property scale, when you move into the city, you expect the city to take care of everything, right? They take the garbage, the sewage, everything is done for you. And what we're now arguing is the house owners has a responsibility to help stormwater management because the city can no longer cope. So traditionally, drain and remove. And at the watershed scale, build structure to protect yourself. And what we're now saying is, why don't we start retaining water at your property scale? Do something very different at the neighborhood scale, because then you have to deal with roads and parking lots. And then at the watershed scale, you have to do something else because you deal with the cumulative effect. So here are some of the ideas what you can do at the different scales. So at the property scale, we can have a green roof. We can have roof water harvesting. Thank you. You can have pervious pavement, because you guys like to pave everything, right? You want everything clean. Why not have pervious pavement? We should encourage everybody to have at least 30 centimeters of topsoil before you put your lawns on there. And I'll show you why that's important. You can encourage tree planting, although this might not be a great idea for Calgary, and I'll tell you why. And we can create all kinds of rain gardens. So if everybody would do that, we could actually help stormwater dramatically, and I'll give you the examples later on. At the neighborhood scales, that's totally different problems. I'm advocating smaller roads, and now you're telling me I'm totally cuckoo to tell you you have smaller roads because you've got a huge traffic problem to start with. But think of your neighborhood. We're now putting obstructions in your neighborhood that people can't drive through that fast. Why don't we have smaller roads to start with? Why don't we remove manholes and gutters? Why don't we let all this water from the road go into infiltration system? Why don't we use wetlands, which are the best storage and filtering system we have? They're far better than all the artificial things we do. We also have all kinds of new materials which you can actually pave the roads that the water can actually penetrate. And we need to deal with parking lots in a totally different way. You probably never look at a parking lot, you just want to get the hell out of there. But go and have a look after about 10 days of rain, no rain. You know exactly where your engine is parked, but there's a little bit of an oil and grease slick there. And what do we do when it rains? The first 15 minutes is so polluted that the fish cannot survive. So if I would like to kill you, which I don't want to do, I give you a high dose of arsenic and you're gone, right? Or I could prolong your life and say, I'll give you a little bit and a little more and a little more, and you'll survive for a long period of time. So think of a fish. What we're doing now, the first 15 minutes of a runoff after dry period, we give them a shock, an electric shock, and then everything is okay again. That's what we do to the environment. So why not start addressing the pollution in stormwater management? Because right now we have never dealt with pollution. We just pipe it into the stream and hope everything is taken care of. And then at the watershed scales, we need to have much bigger riparian buffer zones. We need to have a complete naturalization of streams, and we need to have wetlands within the buffer zones, and we need different zoning, and we need a completely new approach for flood protection. And I'll show you building structures is no longer sufficient. So we actually did a video, you know, when you're retired like me, you can mess around in all kinds of things which you don't know anything about. But when you have students, they can help you do that. So we did a video, and I'll give you the link later on all the innovations which are taking place in the Vancouver area, trying to show people, yes, we can actually do something. And actually it is working and it's cost effective. So you could click on each one of these things on the web and it will go right to the video and show you what they're actually doing. So we can measure impervious surfaces quite easily, particularly if you have diligent graduate students, they can digitize that for you, right? So let me show you initially a classic example of urban water pollution. So here is Burnaby Lake in the middle of the city, and there is a lake in the middle and all the stormwater goes in there, and every year we get a layer of sediment. So we cored the lake and we used isotope to determine the age of each layer, which is an annual layer. And then we can give you this record. We were able to get down to about 1700. And this is the amount of sediment which has come in by layers. Here we had a big storm, and there we had a massive storm which brought a lot of sand, so a much bigger layer. And then we looked at all the metals accumulated in this, and there you go. So we can now show you the whole history of urban management in terms of water pollution, where in the 1800s nobody was there, we had no lead. Then they cleared the forest, and there was a little bit of lead from burning the forests. And then the cars came in the 20s and 30s, and you see massive increase in lead in the sediment. And then we took lead out of gasoline and see what's happening? Going down. So there's the whole history of how we do stormwater, increase the stormwater pollution problem. And if you look at zinc and copper, those are all from automobiles. The zinc is from tires. A lot of zinc, if you break a lot, you get a lot of stuff sink at the road surface, and that all goes into the sediment. But lo and behold, a more interesting thing is, in this lake, we actually still have DDT and PCBs, which we banned in the 50s and 60s. So we can still show it to you where it is. So now the lake is silting in, and in the summer you only have that much water. So now the problem is we want to rehabilitate that stream. So what are you going to do with all this contaminated sediment when you have this kind of pollution in it? So we need to start dealing with that. So we now work with the Water Sustainability Group. It's an NGO partnership, and we do a water balance model for urban environments. So we can actually calculate how much water is generated from your property. And then we added some fancy engineering modeling, the Qualheimo project, which routes the water through your neighborhood and into the watershed. So here is what we do. So now we deal with the property, and remember, you now have a responsibility to help. And this is what you can or should be doing. Here's the Mountain Equipment Co-op building. They built a brand new building. And what they did is they collect all the roof water, they drain it into a swale, and I'll show you what a swale is like. It is in a floodplain, which is all sand and gravel, so the water goes right into the aquifer. They pump the aquifer up and use it to flush the toilet. That's very attractive for the business because they can say, look, we're doing green things, we're doing improvement, and they are leaders in this. They now build a second building also with this kind of stuff. Green roofs, not for everybody, but definitely a possibility. Not only does it absorb a lot of water, but it also reduces your pollution, because remember, all the cars generate a lot of nitrates, and obviously the grass likes that stuff, so it actually reduces the pollution. We have a very intensive agriculture area in the Lower Fraser Valley, and we figured that the animals, you know, livestock, pigs and cows burp about 19 times a day, and they excrete quite a lot of methane, to the point where about 20 kilograms per hectare of nitrogen is actually returned by atmospheric pollution in the Lower Fraser Valley. You know, a typical corn production is about 120 kilograms of nitrogen per year. That's 20 kilograms is a massive thing. A green roof can actually absorb most of that stuff. So, first of all, disconnect your roof water, because everything is going right into your drainage pipe into the river. I have disconnected all mine. And you can actually make a bit of an improvement in your soil that it can be absorbed and won't flood your basement. A much better thing is, why don't you have a roof water harvesting system? It can be a small one down here. This is a big one, and this is a really big one. And you can actually do some really interesting things with roof water harvesting. Bowen Island has a real problem. They have only a small lake for drinking water, and their groundwater has arsenic in it, so they can't use it for drinking water. So they have a bylaw where nobody is allowed to use domestic water for outdoor purposes. So if you want to have a garden, you have to have a roof water harvesting system. And this guy actually decided he's going to flush his toilets with the roof water. So he calculated that one of these containers is enough to flush his toilet for 1 year. So I calculated, I have a very old house, and I used to have these old big flushes, and there were 21 liters of flush. And if you get older, you go more, right? So I flush about 7 times a day, and that's about 150 liters. With the new flush, it's 21 liters for the same thing. So you could save 100 liters of water per day by simply having low flush toilets. Very easy to do. Why don't we have a national bylaw that every new house has to have it? Maybe you do in Alberta, we don't in BC, and it's not expensive. And an interesting way of doing business. We did water harvesting all over the world because everywhere I work, there is a wet season and a dry season. In the Himalayas, you get all the monsoon within 3 months, and the rest of the year you have no water. So we built these underground cisterns, and typical academics, they come with these bright ideas, only to find out that's really stupid. Why would you build an underground cistern in the Himalayas where you get lots of earthquakes? So we learned our lesson, and then simply what the farmers now do, they just simply dig out the pond, line it with plastic, and collect the water during the summer or during the monsoon period, and then use it during the dry season. And you can store a lot of water, but enough water to do drip irrigation, and that's been very successful. Or you can do it for drinking water. We had a project in the Sahara. They had to settle 100,000 Bedouins because they could no longer migrate into Sahara because Libya was closed and Sudan was at war. So they tried to settle them between Alexandria and the Libyan border. This is an area where you get maybe 5 storms a year, about 200 millimeters of rainfall. They already had these underground cisterns, and we calibrated them. We wanted to figure out how big would the catchment area be to direct that water into the underground cistern. And lo and behold, they were successful enough that they were able to settle 100,000 Bedouins to provide sufficient water for drinking and animal use over the summer. And right now, there are about 100,000 of these cisterns. And you can actually see them if you go to Google Earth, because it's all limestone. So it's very easy to dig out and cement. And the limestone is white, so they pile up all the stuff on the side. And so this is a huge contrast to the lot of the rest of the image. So you can actually go and count it. So roof water harvesting has been practiced all over the world. Why don't we use it in the urban environment? The other thing which is really interesting is green water management. So if you work in a desert, the rain comes through, it just is gone within a few hours. These waters are just dry within a few hours. If you put these stupid little barrages in there, you can hold the water back for 1 or 2 days. That allows the water to infiltrate into the soil. That is enough water to grow a crop of barley. And that's what we learned because we were able to do enough water harvesting for animals and people, but they wouldn't give up their animals and they overgrazed the area. So we said, well, how could we actually improve food production for the animals with green water management? So this is what you do, right? Everything has to be paved, and the bigger the better. And so why not do something like this? I had to go all the way to Bolivia to find something like that. And this is in France, and then we have all these things. Now, where is your engine parked? Your engine is parked right here, right? So what happens to the oil and grease and all that stuff? Goes into the soil. What do the organisms do in the soil? They're breaking down the hydrocarbons. Very effective way. The soils are a wonderful media to actually clean up all kinds of mess for you. Everybody wants turf, including Calgary. I have been arguing about this for all my life and I make no progress. So there is this preoccupation that you want to have the absolute greenest, nicest lawn year round. Have you ever thought about why everybody wants this green front lawn? I have an explanation, but it's a pretty stupid explanation. But maybe you will agree with me when I tell you. Your eyes can see from red all the way to blue, right? You can differentiate more green shades than any of the other colors. And that might be one of the reasons why everybody wants to have this green lawn. So what do we do when a new house is being developed? The first thing we do is we remove the topsoil. And then we bring in the bulldozers and compact everything. And they build the house. And what's the very last thing you do before you sell it? you roll out the turf. That's that much soil, right? If you do that, your irrigation requirements goes up by at least 50%. So we now have a number of municipalities who have a bylaw which say 30 centimeters of topsoil is required before you put on the turf. That means you don't need to irrigate very much. I have even a better idea for you. Have a ban on watering your lawn from July and August. Because once the first or second rain comes, it's green again. And my wife told me the only way to convert people is women like jewelry. They like gold, right? So why don't we persuade people to say a golden lawn is actually quite nice? So yeah, you could do all kinds of things. You could do xeriscaping. It's not everybody's interest, but basically cut down on your lawn, because do you like to cut this bloody thing all the time? And then you fertilize it so that it grows faster, and then you over-fertilize it and use pesticide, and all of that goes into the stormwater. Why not just let it go naturally and don't irrigate when you need to? So this is in Vancouver when they started banning. Now let me tell you this stupid story. So they said, okay, we're in a water-short area now. Let's ban water irrigation for lawns. And if your neighbor doesn't conform, please report. Am I going to pinch on my neighbor if I want to have good relations? I'm not going to do that. So they sent out police guys to do this. Crazy. So we now have smart water meters. So you can actually sit on your computer if you have smart water meters, and you can find out from every individual how much water they use at any day, and you don't need to go and inspect anything, and you can actually tell them, I give you a warning, and if you don't conform, I fine you. All on the computer, you don't need to send anybody out. Why don't we get there? Water metering is changing in a way which the technology is changing. And we have an interesting situation in Vancouver. We're not metered. Though, can you believe we're not metered? I can use as much water as I want. It costs me $500 a year. And we've been telling them we should meter. And they say, no, we bring it in over time. So now think about it. They started this 10 years ago. It's going to take at least 30 years before all the houses are renovated. Well, the technology which they used 10 years ago is totally different. So by the time they get to 20 years, they're going to have to replace the meters anyway. So why not do it? So why not do a green garden, something like this? This is one neighbor who decided he's going to have a rain garden, and it looks incredibly attractive, and it's been a huge success everywhere. Everybody wants to come and look at it, and he's infiltrating all the runoff from his house. So we didn't know what urban trees can do. So we decided we would do a study in North Vancouver, which is about the worst place you can do this. The airport in Vancouver gets about 1,500 millimeters of rain per year. North Vancouver gets 3,000, okay? And it all comes in the winter. And we urbanize, we have no place, we have to go up. So we said, what could urban trees actually do? Well, you look at the forest, and a typical forest evapotranspires about 20 to 30% of the rain. So if you have a forest, the rain hits the trees, and about a third of it gets evapotranspired. But urban trees are totally different. They're open, the wind blows through it, temperatures are higher, so we figured they must evapotranspire more, but we had no idea. So we did a study. We had a student, we built all these crazy interception systems on 55 trees, and she studied it over a year. And here's what she came up with. She came up with Douglas fir and cedar can reduce about 50% of all the rainfall which hits the tree. And not only does it evapotranspire, it also, when the rain goes through, it delays the runoff. So now we're telling everybody you should have a tree on your property, you should get carbon credit, it will cool your summer temperatures, and it's very good for stormwater management. Now this might not be a good idea in Calgary, because you might have to irrigate your tree in Calgary, which we learned the hard way, but in other parts this is a very good solution. Just to show you how effective some of these trees are, you can see how much of the snow they intercept. And so if you now look at your watershed and you look at all the forest up there, you could actually manipulate the forest to do two things. In a drought, you want to encourage water, and in a flood, you want to detain it. And there are all kinds of ways which I'll show you later on when we talk about the watershed, how you can do that. So now we go to the neighborhood. So in the neighborhood, you can see all the pollution problems in the manhole. And here's a classic example of a neighborhood where you have a driveway and a garage, yet everything is paved and everything is washed into the thing. Why not build roads where all the runoff goes into a sand filter and all the pollution gets taken care of? Not all of it, but quite a lot of it. So you build a road with no pipes, the runoff goes into the sand filter, and this is how they look. So we built these compartments, fill them with sand and gravel, and then you don't need to grow a lawn in it because there's always water percolating through, so the trees will grow by themselves. You don't need to irrigate, and it looks much, much nicer in terms of the neighborhood. So here's the road, and here's the walkway, and here's the drainage system. So we have now a lot of these kind of system happening in new development. If you get into a new development and you do it before all the planners and everybody else goes in, and you protect these areas, you can actually do it. Here's another example, some very small innovations, having the runoff go through filtering system before you actually put it out. Here's a nice example. The only sustainable street we have in Vancouver right now is Crown Street, where all the runoff goes into sand filters, and the bottom, the reason why we did this, the bottom of this road has a nice salmon spawning stream, and we've been monitoring the stuff, and we virtually get no pollution coming into the creek as a result of it. The only thing you need to be careful about when you have these roads with no curbs and no gutters is over time the grass grows up, and then the water is actually stopped. So you need to kind of clean it every so often so that it doesn't stop the rainfall from infiltrating. And this is the ultimate kind of neighborhood which we're talking about, which looks extremely nice and does a very good job for stormwater. That gets me to parking lots, and so what we do now is something like this. Here's a parking lot. We put in a sand filter. The runoff goes in, it's delayed. The organisms and the bacteria in the sand filter are actually breaking down some of the contaminants. I had a student looking at these sand filters and wetlands, and she measured over a year what's coming in and what's going out, and we're reducing the pollution at about 50% for metals, and we're also reducing the flow dramatically because it's delayed. It has to go through all the pores, right? That's green water management. You can do these kind of things. In fact, this one is a really interesting one. I don't know whether you can see this. Here is an awning, and they grow willow. And what they do is the water goes into the infiltration system, the willows grow, and they train the willows to go over to create shade. So it's going to help you with CO2 absorption. It helps you with stormwater, and it gives you a much nicer experience in your parking lot and cools your temperature. Nice way of going at it. And then, of course, all these pervious materials are now pretty effective, and they really work well. We now have concrete, which actually is pervious. It's a bit more expensive right now, but it works. We have now 2 lanes, which we experimented with, and the water can actually penetrate. So this is typically what we have traditionally been doing. And now we're building wetlands in the city. We were responsible for at least 5 of these constructions with students. And you can't imagine the kind of battle we have been waging. Because the very first thing which happens when you go into a neighborhood and say, I'm going to build a wetland. We don't want West Nile virus and mosquitoes and Zika viruses and everything else. Yet, wetlands are the best storage system for water and the best filtering system, so why not use it? And so here's some examples. It is very tricky to build a wetland so that it is functioning properly for urban stormwater management, because it's very easy to drain a wetland. It's much more difficult to actually create one which does all the right stuff. We built about 3, which took us about 6 years to get it right. But what's even more interesting, here's one for a whole neighborhood where all the stormwater from the whole new development goes into the wetland. And we now discovered that the best way to do it has 2 wetlands in sequence. One to absorb the big stuff and the other one to polish. And we also built a sediment trap before the wetland. And this has to be cleaned out every 5 years. And in a process, you store the water and you filter it. So now we get to the problem of mosquitoes. So a colleague of mine by the name of Michael Jackson, he's not the singer, he has a company, and this company is called the Mosquito Company. Did you ever think you could make money fighting mosquitoes? Well, he has now the contract for all the city wetlands to make sure that we don't have too much mosquito problems. So what does he actually tell you? He tells you that here's what you can do. First of all, make sure that your wetland has never completely stagnant water. Always make sure there is movement. And the way he does that, he's putting a solar panel or a windmill on there. And so the water is always flowing. Mosquitoes don't like that. They like stagnant water. The second thing, they don't like eutrophication. Or the mosquitoes like eutrophication. And so what he's advocating, if there is a problem with eutrophication, first of all, stop the nutrient inputs, and secondly, clean it out once a year or once every other year. The next thing he says, use a wide range of plants and plant them in such a way that there is space between the plants so that UV light can get into the water. And the UV light is, again, a thing which mosquitoes don't like. And then create a variety of plants, because some of them are antagonistic and they can actually help. And then the last thing you can do is put in stickleback. Stickleback fish can actually tolerate some really nasty conditions and survive quite well, and they eat all the larvae. And so if you go in there at the larvae stage and you do a little bit either with pesticide or with scraping, you can actually reduce the mosquito problem quite dramatically. So here's what he does with stagnant water. Here's what he does with eutrophication. Here's what he does with planting all kinds of different species. And here's the kind of fish he puts in there. And it's been incredibly successful. And the idea behind it now is, how can we present that to the public as an alternative situation to help stormwater management? This is a really bad one. I thought I should show you some really bad ones. This is not a wetland which is going to work very well. So here's a new neighborhood. So what do we do? So here's a plot, right? This is one lot. And so they built a 2 by 2 by 2 meter hole. They filled it with sand and gravel. That is then connected to a sand filter. The sand filter is then connected to a pond for the very high storms. And this is before the development, and this is after the development. So here are the houses, here's the sand filter, and here's the pond. And this is on a sloping terrain, so this works actually quite well. And this is the pond which will hold back these very large storm runoffs. So that gets me to cul-de-sacs. Everybody loves these roundabouts. You know, the kids like to skate around and so on. And so we have different kinds. This is the classic example which we use here. And then we get some landscape architect to put some nice flowers in it, right? Or you could make it smaller, or you could make it in this design. Have you ever thought how much of the impervious surface you could reduce by going from this to this? You can go from 420 square meters to about 110 square meters. Massive reduction in impervious surface. Of course, the very first thing they will tell you, well, that's no good for fire engines. Well, the fire engines have to get in fast. They don't have to get out fast. And going to a T-shaped system is probably good for you because you get a bit of exercise, right? So now we go to the watershed. And now we're dealing with all this integration of all these activities. And so buffer zones is a really big thing. We have a law in BC, I don't know what it is in Alberta, 30 meters. 30 meters on both sides of the river, riparian buffer zone. Well, so you look at this, all the green is the green areas and all the rest is impervious surfaces. And then that's the buffer zone. So what the science is telling us is if you want to have a really good buffer zone, it will help you with noise reduction, it will help you with temperature reduction, it will help you with sediment removal, you will have space for wetlands, and you can actually have a lot of pollution removed within the riparian zone, and you can have all kinds of biodiversity. But if you want to do all these functions, you need at least 60 to 100 meters of a buffer zone. Now, you couldn't do this in the middle of the city when it's already developed, but you can do it in every new neighborhood. And we should have actually a law which requires every development to have at least a 100-meter buffer zone. And why do we need a 100-meter buffer zone? There's 3 zones in your buffer. The first zone is whatever runs off the surface. Remember that first diagram? The forest allows about 10% of the rainfall runs off the surface. Then some of the water goes into the soil and seeps laterally into the stream. That needs more space. And then some of the water goes into groundwater and seeps into the creek. So the bigger the buffer, the better off you are. So those are, of course, examples which are not very good, because if you put the river in a channel, all the water can do is come up. It cannot go sideways, it cannot meander, it cannot dissipate energy. And so what we should be thinking about is not this kind of stuff, but something like this. Meandering systems, naturalizing systems. So this is a very nice buffer zone in the middle of the city where the water can actually go sideways and up and down and everything else. Those are good buffer zones. And this is, of course, a very bad one. So we're actually doing this. We have channelized many, many rivers, and now we're saying, well, why don't we go back and renaturalize these streams? This is in the Okanagan, and you can see, here's the channelization. And now you can see all the oxbow lakes and all the stuff. Now they have opened this up, and they have created so much biodiversity, and salmon are returning, and it's been an incredible success story. And simply, they have had enough space to actually do this, to re-engineer the stream into a natural stream. So how do we deal with flooding now? All we have ever done is build dikes and structures to prevent you from flooding, right? And have zoning laws that you're not supposed to do that. So what I'm advocating now is, why don't we use every topographically alternative area in your watershed, which is not being used extensively, and use that to store water during these peak storm events. It could be a golf course, and you can tell how the golf people like me. It could be a park. It could be an agricultural area, something like that. And here's the example. Here's the Mississippi. And in 2011, they predicted a huge storm. And they were saying, we're going to flood 2 communities with 8,000 houses. So they decided, so why don't we breach the dike right here, inundate all this water in this agricultural area, leave it there for 2 weeks, and then release it later on and compensate the farmers. They were extremely successful to the point where the farmers were back in business 4 months later. The only problem they had is there was a lawsuit, and that delayed the breaching by about 3 days, and by then the river was much higher, had more velocity, and created a few deep channels. And then that was much more difficult to relegate. Now, the Red River was flooding that year as well, and they were going to, you probably remember, they were going to deliberately flood 500 houses, and you can imagine if you're the house owner and the government comes to you and says, we're going to flood your house, you're going to get mad, right? They went out 24 hours before the flood, before the breaching, with GPS to figure out where the water is going to go. Why don't we do this right now? We should go and say, okay, where is there either an agricultural land or a park or whatever in your watershed all the way up to the Rockies, and find out where are some of these areas where we could temporarily store the water. It doesn't cost you very much. It's not, I mean, you're not going to build massive infrastructure. I've looked a little bit at what they're doing in Canmore, and I was just couldn't believe what I was seeing. Complete cementing of your channel. Why don't we start thinking about these kind of things? Because they are probably much cheaper. However, when you work in the Himalayas, I've done in about 14 years, when you get these kind of systems, there's nothing you can do. You just need to leave the floodplain as wide open as possible. Don't allow any development because you can't stop it. But in your case, I think you can do quite a lot. So in the city now, we're looking at opportunities of where to put in wetlands. And so, for example, here's the area which we know is going to flood. And here's an area which we're going to flood. And here we can actually look at, here's an area where we can put in a wetland. And we're building these kind of things now. So here is the biggest challenge we face. How do we get these ideas into mainstream when the engineering profession is very risk averse? You know, they basically know what they're doing and they know what it costs and they are very efficient in what they're doing. And if you come with a new idea, they say, wait a moment, what's the liability? How much is it going to cost? What are the long-term management problems? So how we persuade this concept of urban stormwater management from an engineering to a more naturalized approach? So here's what we do now. Here's an old house. It was redeveloped, and we went from 28% imperviousness to 53%, right? So we now have the water balance model and say, before this house was developed, the old one, this is how much water ran off that property. Then there's the old house. This is how much more it generated because it had more impervious surface. And this is the new house. So if you now do any of the 7 things I mentioned to you, roof water harvesting, green roof and all that on your property, you can get down to here or down to here or down to here. In fact, I am now convinced we can get better than what was there before the development, because we're helping the soil development, we're helping all kinds of things. So give me another example here. Here's an old house, was redeveloped in a subdivision. It went from 23% to 54%, and here's what we can actually do. So how do we get people to buy into this? So we looked at the whole urban watershed and said, okay, How many houses would have to do this before we see a response in the watershed? And how can we convince people to do that? So we have an opportunity now. In North Vancouver, the houses were built in the 70s. You can see all the blue bars. This is when the house stock was built. And so the houses are like me, they become old and decrepit. And so there will be a massive renovation coming place in the next 20 years, starting about 2020. So when they start renovating, we should be in place where we can have bylaws to enforce that they have to do something, right? So how we're going to go through this transition between now and 2020 to persuade the public that this is a good idea and the governments that they should buy into this. Whoops. So what we're trying to do is we now have a website for North Vancouver where all the properties are on the website. The public can access it. It's a beta version. And you can then click into your property and it will tell you how much impervious surface you have and how much runoff you're generating. And then we have a scale like in the forest system where we have red, orange, and green. And then you can play and say, what if? What if I do a green roof? Could I get from red to orange? What if I do a rain garden? What if I do roof water harvesting? What if I do this and this and this? And we're hoping that over the next 3-4 years, this is kind of a game. We're training the public to use it as a game. And then once this new stock of renovations comes in, maybe we're ready for bylaws and say, okay, and we're not going to tell people you have to do a green roof. We're simply going to tell them you have an option, but you need to do any one of these kind of things. So that's the kind of things which we're challenging people to do now, because the frustration to me is you are willing to accept all the new technology in your cell phone. Nobody questions that. But when it comes changing your attitude towards urban stormwater management, there is so much conservatism involved. And we need to change because of the climate, right? And the land use. So I am going to do some acrobatics now, hopefully. And see whether I can get in here. So now we need to also go to the rural part, not just the urban part, because the rural part is equally as challenging, right? So, see if this works. So let's see actually how we can actually protect and enhance the environmental services in the watershed, and how we can actually kind of help the environment to improve what we're doing. So these are all the natural environmental services which a river provides. Obviously, it provides material water for people and food. It has social value. It has regulatory value. It cleans up the water, and it supports all kinds of things. We have a real problem trying to calculate how much water should we leave into the river. You know, at low flow, what would be the minimum flow which is good for the environment? This is incredibly challenging. These are the main methods we use, and neither one of these methods is very easy to do or very good. Some of people just look at the width of the river and say, well, we should do this and this and this, and it's not very good. The economists don't help us either. So what we're now saying is we should actually leave about 70% of the natural flow in the river. In other words, don't just worry about the low flow. Worry about 70% at the peak flow and the low flow. And that's a very difficult challenge because we have given people lots of permits to take water out. So the economists don't help us very much either, because these are all the methods which they use. And most of these methods are not particularly enlightening. Willingness to pay. What a fantastic economic assessment. How much are you willing to pay to maintain a bear? How much are you willing to pay to maintain a wetland? That's not a particularly good way of doing things. So here are the direct incentives which we could use to actually help the watershed and the environmental services. We can have regulations, we can have economic incentives, we have to have governance issues, we can have technical and social things. These are all innovative ways of doing this, but we need to get buy-in. So, green water management, I'm hammering you with green water management. Green water management is the way to go because soils and plants can help us with this stormwater issues quite dramatically. So, mountain forests. Have you ever thought what you could do in the forest up in your headwaters to either increase your flow or decrease your flow? So if you have a drought, you rely on snow melt, right? How could we actually manage the forest management to increase the snow accumulation? If it's a complete forest, the snow accumulation is actually much, much smaller. If you clear cut, you get more snow, but apparently that's not a particularly good thing. All the research is telling us what you should be doing is small patches, open patches in the forest. That can accumulate at least double or three times the amount of snow which you can accumulate. So that's very good for drought. Might not be very good for flooding, but that's a good management practice. You should also have multiple types of trees because what we're learning now, like in agriculture, we know for every crop how much water is used. We really don't know very much how much water is used for individual trees. In fact, some trees are really water pumping and some trees are very water efficient. And it's interesting that very few people have actually focused onto this because of the temperatures, the forests are moving up into the higher elevation, and we're now contemplating, should we help this process? Should we bring plants or trees from lower elevation to higher to help to speed up this thing? But we never look at how much water they consume. I was working in a project in Ecuador, in a mountain area, and a Dutch businessman came up and said, I'm going to propose to lease all your farmland for afforestation for carbon credit in Holland. And we pay you rent more than you make a year, and you can work on the plantations, and we give you a 30-year contract. And then we ask him, so what are you going to grow? Eucalyptus, the most water-intensive crop or tree. So we need to look at water consumption by trees, and in those areas where you have a lot of seepage, a lot of water coming out, we should put in trees which pump out a lot of water. And in those areas where you don't want to do that, you have other trees, right? Increase the organic matter in your soil. We know, and I'll show you an example, we now know that 1 gram of organic matter can hold 1,000 times its weight in water. It's like a sponge. Remember when you put a sponge under the sink? First 2-3 minutes, no water flows out, everything is stored. That's organic matter. And I'll show you an example how we can actually increase that. So tree water requirements, and then the riparian buffer zone, because that helps you in many ways. And then, of course, in the agriculture area, we need to start also thinking how we change the soil carbon, because you have done an incredible job reducing the carbon in agriculture in the soil. When the prairies were not cultivated, when they're under native grassland, the carbon organic matter content was about 16%, 15-16%. Guess what it is today? About 4 to 5. So we lost 2/3 of the carbon in the soil. And we just organized a workshop in November in UBC. How can we sequester CO2 in the soil so that we can store it as carbon so that it actually holds the water and helps you maintain the water? And so agriculture practices can actually do that. They can increase your carbon content, and I'll show you some examples. Irrigation efficiency, you guys in Alberta have done a phenomenal job in reducing your irrigation requirements. I was astounded when I went to the workshop with the agriculture people. My hat is off to them. They reduced their water consumption by 40% in 5 years. That's phenomenal. Efficient irrigation. Minimize soil compaction, because remember, the water stays in the pore space of the soil. If you compact it, that pore space is reduced. You can't hold it in there. And water harvesting and storage. So the infiltration rate changes very, very quickly. So the green line is how much water infiltrates over time after a storm in a forest as opposed to an urban environment. And you can see how much more water can be infiltrated in a forest than in the agricultural land. So I showed you this. This is a very simple example on how you can actually encourage water to infiltrate. So this is actually data from Alberta, and it shows you in green how much carbon was in these different soils at the time they converted it into agriculture. And this is how much is there now in cultivated areas. And you can see how we have reduced the carbon content. Now we try to store CO2 in underground geological formation, spending millions of dollars, which is the biggest nonsense I've ever heard. Because first of all, underground systems leak. And secondly, the energy it takes to concentrate the CO2 and pump it in is so expensive, this doesn't make sense. But we could actually encourage the carbon content in the soil to actually do that. And so we could enhance the carbon content by adding manure. Remember, you have all the manure concentrated in one area, and you can only ship it about 50 kilometers. So we should have an incentive program to take, now this is crazy again, but academics can say that, right? Why not ship the manure in the surplus area to the non-surplus area to help the carbon build up? Reduce the tillage, because every time you till, you aerate the soil and you break down the carbon. Growing nitrogen-fixing trees or nitrogen-fixing crops will help you create biomass and organic matter. And guess what? You got limestone in the mountains, right? Limestone conserves carbon. This is a soil which we did some study on in the Yukon. And you can see how much humus is in this soil in a semi-arid environment, because the limestone, the carbonate, the calcium carbonate, binds with the carbon and maintains it in a much longer period. So remember, here is all your manure which you're generating. You have to bring this into areas of grazing land to help the carbon content. Trees, I already mentioned we should look at the water content in trees and obviously the buffer zones and the rezones. And here's another good example of what not to do. Look at agriculture. We always go right up to the drainage ditch. And so basically everything goes right into the same. So in the urban environment, we should have much better buffer zones, and in the agriculture area as well. Now, once you already channelized your river, it's going to be extremely difficult to re-engineer it. This is a case in Switzerland. In Switzerland, they have channelized every bloody mountain stream. And now they're saying, oh, that was a big mistake. So now they're trying to re-engineer the stream, and the land is so expensive, so wherever they get an opportunity, they buy the land and create something like this. But one of these examples will do nothing. You need a massive idea of how to do this, and this is not going to be easy. So don't do it if you can. The other thing you should remember is the processes in river water management in the headwaters is totally different from the lowland. Remember, in the headwaters, everything is connected to the stream. So erosion goes into the stream. In the lowland, it's not the erosion, it's the resupplying or the resuspending of the bed and the banks. And so the processes are very different. So we should protect the mountains in a different way from the lowland. Pools and riffles. We say if we want diversity, create pools and riffles. This is artificially done on there, and this is naturally done. By creating pools and riffles, you disseminate the power of the river, you create habitat, you can enhance all kinds of things. Wetlands. We can encourage and improve wetlands all over the mountain areas. There's lots of space to do that. And I don't know why we don't like wetlands. I guess if you read the British literature on Scotland, the moors and the wetlands are nasty. People have disappeared. You can't walk through it. There are ghosts in it. And guess what? They smell. Have you ever dug into a wetland? You can smell the hydrogen sulfide, right? So we have a complete negative attitude towards wetlands, and yet we should actually have a much more positive attitude towards it. Here's a good one, which we're enhancing up in the mountains. So the next thing you want to do is, we know that the river water is increasing. The temperatures are increasing because of climate change, and if we want to have fish of certain types, how can we actually cool the river? If you have a glacier, that's perfect because that provides cold water in the summer. Once the glacier is gone, you don't have that. So here's an example of winter temperatures. So the gray is rain on bare ground. And you can see when there is rain on bare ground, the temperatures are very high. When there is snowing in red, or when there is rain on snow in blue, you can see the temperatures change quite dramatically. That's in the winter, but then in the summer, all the things we try to do is building trees to cover your small first and order and second order watersheds. If you grow the big trees, they can shade your stream and they can actually reduce the temperature. And the studies I looked at, we can probably reduce the temperature by 1 to 3 degrees. So that's not great, but it helps. But the second thing you can do is, why don't you do an inventory of where all the groundwater comes into your watershed? We now know in BC, all the great salmon spawning habitat is in areas where groundwater comes into the stream. If you go to the Adams River run, massive groundwater coming in, it's cool, fresh water. We should do an inventory from the bottom of Calgary all the way to the top and find out where are all these groundwater aquifers which bring in cold water, and preserve those. Don't let them use them, because that will help you cool the water. This is relatively easy to do because all you need is a thermistor and go all the way up and find out where cold water comes in. Is easy to measure. You can also do it with isotopes. The other thing which is interesting, actually, hydropowers can actually help you quite dramatically with temperatures, because you could release water from the hydropower dam, bottom water, which is cool, and release it at the critical time. If you have a drought and it is going to be really hot in terms of the water temperature, why not force the hydro companies to release water to cool the system? In the European OPPs now, they require all the hydro companies to release water in July and August at certain times, not only to cool the water, but also to reduce the pollution. Because if you don't release water when it gets lower and lower, concentrations go up. And if you have a hydropower system, you can actually do that. And the new systems can release water from the bottom, which is cold. You still with me? I had an opportunity to talk to one of the big engineers from the biggest hydro company in the world, And I was asking him, so all these new activities, where is the big deal? Pump systems. So what they do is they build a reservoir on top and a reservoir on the bottom and the system in the middle. And they produce electricity only for peak power. This is one of the examples. So from 6 to 9, from 11 to 2, and from 5 to 8. And then the water is released into the lower reservoir. And then at 2 o'clock in the morning, they buy the cheap power to pump it back up. They make huge amounts of money in Europe because the prices, the peak power prices are totally different. And he said, this is the biggest push right now. He said, the costs are minimal, the profits are 500%. And in Europe, they buy cheap nuclear power from France, which nobody uses at 2 to 4 in the morning, and then they produce that. This is great for electricity, but might be a huge problem for watershed management, because then you're actually recycling the water in the upper part without releasing it. So be very cautious when they propose that in your watershed. So I showed you this. So the traditional approach has always been engineering structures, and now we're saying, why not use nature and learn from nature to do this? So, oops. So here's some of the rehabilitation or restoration which we can actually do to enhance the system. We do this with a lot of community groups in the city as well as in the rural environment. We have a lot of salmon NGOs and so on. And so we're actually involved in many of these things, and we do the science for them. And so you could have overhangs on the river so the fish can hide underneath it. You can have marsh benches. You can have side channels. You can stabilize all this kind of stuff. So here's an example where you can enhance the banks. Here's the design, and here's actually people doing it. Or here's another one, creating a side channel, which is really important for everything, for not only accumulation of sediments and so on, but also for fish and everything else. Here's the example, and here is the action. Sediment control is a big issue. So let me just show you an example how you can actually rehabilitate some really degraded sites. When I first looked at this, I said, oh, forget it. And then the students came and said, well, we need to do something. And I said, well, gee, I'm too old, because by the time I rehabilitate this, you know, I'm over the hill. No, we need to do this. So guess what we did? We said, okay, we're going to do some rehabilitation. The first thing we're going to do is we're going to lime these soils a little bit because they're all acidic. Red soils are acidic. So liming helps the organic matter to be retained better, right? The next thing we said, okay, why don't we do agroforestry? We want to grow trees, but what kind of trees would you want to grow? These soils are totally depleted of any nutrients, and nobody in their right mind would pay money to go and fertilize these things. So we said, okay, we're going to grow nitrogen-fixing trees. And we're going to do an experiment in the lab to see which one of these trees takes on mycorrhizal fungi, which is a fungus in the tree roots which convert phosphorus in an unavailable form into available form. And then we said, we only want to plant native trees in the Himalayas. So we found 25 different nitrogen-fixing trees, which are native to the country, and about 6 took on mycorrhizal fungi. And so said, okay, those are we're going to focus on. So how do you get seeds? You can't go to the supermarket and buy the seeds. So we rented trees for about 2 years because the farmers love trees for animal feed. So they never get to bloom. So we said, okay, we pay $10, leave the tree so we get the seed stock. And then we created a nursery. And then we went from this do this, do this. And it took about 7 years. And why don't we start thinking about this in all these areas which are a bit degraded, which actually have the potential to help nature? And this has been incredibly successful because this particular area created so much problem for irrigation, because every year all this sediment filled up all the irrigation systems. And now we virtually have no problems at all. And now we have biomass, which helps the carbon content, and the women in Nepal collect all the fodder for the animals. And these fodder trees, you can actually cut the leaves every so often for fodder. So we brought in the women and said, okay, once a year you're allowed to come in, take some of this fodder and see whether you like it, whether the cows like it. And if they do, we help you promote this in your community gardens. So here's the experiment with mycorrhizal fungi. And here are the ones which were really successful in green and the one which weren't successful. So how is your stamina? Can you handle another 15 minutes? No? Yes? Maybe? Yeah. Okay. People were telling me I don't have enough Alberta examples. I had this wonderful experience. I was driving from Banff back to BC, and I got stuck in this mud flow, and everybody was ticked off because they had to go all the way to Radium Hot Springs, and I just had a ball. I stayed there for 2 days just watching this. This is the most incredible experience you can ever imagine, because this stuff is like liquid. So the bulldozers come and push it, right? And as they push it, more is coming, more is coming. It takes about 3 or 4 days to actually clear this. It's amazing. So what have we learned from the community process, which we did in the Columbia Basin? We worked with 20 communities and we said, how should you adapt to these new climate norms? Most of the communities said, well, we can't do anything about it. We said, no, you tell us what your issues are. So we learned about what their concerns were, and typical academics, we first went in there and told them what the models tell you. And you know, this is redneck country, right? So they said, oh, you're full of beans. And then we started thinking, we said, well, why don't we just ask them what they think the problems are? And then we learned really where their things are. So we asked them to set priorities for their community and then develop a strategy and an action plan. So these are the kind of infrastructure problems which all communities are facing. These are the kind of priority risks which they're worried about. And then here are the perceptive options. So you can see in terms of the risk, fire, landslide, flooding, drought, and water supply. Those are the big issues. So here's an example of 3 communities. And we said, okay, what are your priorities? What is the extent of your problem? And what kind of initiative can you take? So their priorities were primarily, highest priority is water availability for drinking water. The second was usually fire or flooding, one or the other. And food security was the third one. So this is the framework which we use to encourage them to actually come up with a strategy. So we said, okay, what's your exposure from climate change? And how sensitive is your community to the climate variability? We then said, where in your community will be the greatest impact? So look at Calgary with the flooding. You know exactly now where the greatest impact is going to be. And then you need to start thinking about, do we have the capacity to do something about it? And then you do an assessment on the vulnerability and the probability. If it's going to happen more frequently, Is it highly vulnerable? That's where we should focus on. And then comes risk and tolerance, which is totally social, and then a priority list. So here is an example from, I think it's Caslow, where they identified flooding is the biggest risk for certain buildings. It has very high sensitivity. We have very little coping capacity to do anything about it, and we're highly vulnerable. And these are lower and lower. And then we built this kind of a framework where we said, this is the vulnerability on this axis, and this is the probability of occurrence. And so if you're up in here in the red part, this is where you should focus your attention. If it's on the orange part, that's the next priority, and so on and so on. So we did this for about 12 communities. Here's another one, and here's another one. And so they now have a strategy where they can focus what is the highest priority, what's the next. We have 12 communities have bought into this, and one has put it into their OCP. And the UN has picked it up as one good example to flog around the world on how mountain communities can adapt to climate change solutions. So there's lots of stuff you can do, and I'm very encouraged that this is happening. And now we're into a real interesting project on water conservation. We are still some of the highest water guzzlers in the world. And you think we're conscientious about water? We have done a study in the Columbia Basin. I sent a student around in 2006 to talk to all the engineers in 20 communities, and I asked them, how much water does a person use? Some communities use up to 1,500 liters per person per day. The average in Canada is about 350. So we figured that can't be right. There must be something wrong. So the Columbia Basin Trust then put in some money and said, what communities would commit themselves for a 20% reduction in water consumption over 5 years? And they financed the thing. And 2015 is the end of the thing, and I'm just analyzing the data. And it's fascinating. Every community has done something different. And some communities have such a problem you wouldn't believe. Cranbrook loses 70% of their water in leaky pipes. Fernie, 50%. And they have no inventory, they have no idea what the infrastructure is like and so on, because it's totally neglected. These communities don't have resources to actually do this, right? So if you look at, you think it's very, very easy to come up with conservation strategies, but you have to think of all of these things. Very complicated. And just to give you a bit of an idea, when you look at the temperature, so what I'm doing here is, this is a mean maximum temperature, and this is water consumption. And these are 3 communities. And you can see in the wintertime, everybody uses about the same amount of water, but in the summertime, you can see what happens. Now, these 3 communities do about the same thing, but look at this community here. So you can already see that one community is using massive amounts of water in the summer season. So they should focus on the summer. How about these communities? They're all over the map. So why do these communities have so much water use in the winter? Bleeding pipes. So they don't freeze, right? So what you can do is you can actually go and put a regression into the summer and calculate how much more water each community would use above 15 degrees, because that's when the thing happens, right? And so you can now plot up who is using most of the water in the summer, and you can see these communities use massive amounts of water. That's what they should focus on, right? So you can do all kinds of fun stuff with this. Here's Caslow. 5 years of data in blue, and then 2014 in red. What happened? Why did they reduce the winter consumption and the summer consumption. They fixed a massive leak. So you can actually show people how this works. So the priorities is start to reducing the leaky pipes, install water meters. Nobody wants to be metered in these communities, but we meter everything else, so maybe the time has come that we should actually do it. So, in conclusion, now it bored you long enough. Here's all the things you can do in terms of water conservation. Here's all the stuff you can do to protect the water systems. Here's all you can do about accounting for water. Businesses are also an interesting kind of case study. Every February they meet in Davos on this economic forum. And last year, for the first time, the business community said water is the greatest risk for business for the first time. And this is surprising because one of my former PhD students got his degree in hydrology, and he was hired by Deloitte, which is an accounting company. And I could never figure out why would they hire a hydrologist. Well, his mandate was water accounting for business. And he's worked there now for 7 years, and I asked him the other day, how is it going? And he said, well, I'm spending 70% of my time on carbon accounting and only 30% on water accounting because water is too cheap. Doesn't make any sense, right? But now they're starting to realize that the supply chain problem for water is going to be critical for business, so they will improve their stuff as well. And then, of course, you have all these kind of ideas which you can pursue in terms of stormwater management, and that should help you. And then here's some of the things which, if you're interested in any of these slides or whatever you're interested in, here are all the websites which you can use and download and use whatever you want. You need no credit given. It's educational material. There's also the video on the innovative stormwater management, and all of these are my textbook. I teach web-based courses on watershed management, and last year I hired a young computer geek in engineering to help me convert all these textbooks into an app so that you can access it from any cell phone, any media, and an attempt to spread the ideas. So thank you very much for your attention, and if you have questions, I'd be happy to respond.
So I'll invite any questions for lunch. Maybe just a few quick ones. If people need to excuse themselves, please help yourself. I don't know what we're at if we don't pass away.
I've got a question about, you said maybe Calgary isn't a great place to plant trees because we need to irrigate them. Is there a payoff period? You know, if you look at solar panels, it costs a lot to get them, but at some point there's a payoff period. So do you think you maybe have to choose trees that you need to irrigate for 2-3 years so they're a little more mature, and then you start paying off with their stormwater management?
Well, the biggest challenge we face is how many of these initiatives have to be taken before you actually see a response in the watershed. And I still don't know the answer. Okay. We looked at, in one of the watersheds in North Vancouver, we looked at the idea of saying, okay, we know 7 are doing it, and we monitored the stream flow and we couldn't see anything. So now, obviously, we need more ideas. The payoff period in terms of wetlands is about 3 to 4 years. If you go in there before development, trying to re-engineer the city and wetlands, that's a totally different story. So most of these innovations would be first and foremost cost-effective in new development. And remember, 3 billion people move in the city, so we better get in there before. Look at Calgary, we still have lots of space, we don't, right? Yeah. So get in there right now and make sure, from a government perspective, protect all the water resources before planning and all the development. That's far cheaper than re-engineering cities.
It's tough to get buy-in, though.
Hence my name for a moment. Mark Van Doen, City of Calgary Water Resources. I loved Hans' presentation. This is the one part that I have to refute him on. Actually, trees can be wonderful in Calgary with proper stormwater management within the lots to provide that as water to feed the trees. Of course, we don't want to use potable water for irrigation. That's where proper stormwater management comes into play. So this is the one part which is like, okay, the story needs to change a little bit.
Well, I'm glad you pointed this out because these swales, these are stormwater swales, so they actually provide sufficient water that you don't need to irrigate. So in Calgary, you know, when we had a workshop in Vancouver 7 or 8 years ago, and then in Calgary and then in Toronto, trying to figure out what innovations are taking place and what's going on. And when I proposed trees in Calgary, everybody said, you're crazy, right? You have to irrigate. But now that we know these swales, stormwater swales, actually provide enough water that you don't need to irrigate. So again, I'm glad you pointed it out. Yeah.
Some municipalities have started having stormwater utility charges related to the degree of the building. So you can really talk about that as a management tool. Are you familiar with that? If it work, it's, you know, what it makes.
Well, you know, I think we need some subsidies and we need carers. But people will not do anything unless you have some incentives. And you can tell I'm not good at economics, basically. I don't really know what to propose, but we subsidize so much stuff. You know, we subsidize ethanol, we subsidize the water, we all subsidize natural gas. But yet we don't subsidize innovative ways of doing stormwater management. And I think time has maybe come to do that because a developer will not do anything unless it's going to be less money, right? And so why not have some incentives to get this all rolling in innovation? I am all for it, but I'm talking into the wind.
And maybe just one more question.
With the green roofs and the incentive to encourage green roofs, is there implications in the building code to ensure that those roof structures are sufficient to hold that up? And is that something that should be also explored to help encourage green roofs in other municipalities across the country?
Well, green roofs, obviously, you can only contemplate that in new houses because you would have to kind of reinforce your old house. And the most appropriate place is in industrial and commercial buildings, because then you have large surfaces and that's where you actually are most effective. So there is actually, if you're interested, there's a research place in Vancouver, the Green Water Research Center, and it's by SFU and PCIT, where they do this. And they can tell you all the economics and all the stuff for it. And it doesn't work for everybody, but definitely for big buildings, particularly if they have flat roofs, it's a very good situation.